Welcome, I'm Korbinian Niebler and you joined in for the talk on flame dynamic similarity in a geometrically scaled combustor that I gave at the ASME TurboExpo 2026 in Milan and that you might have missed. The Mona Lisa of thermoacoustics. Maybe not as beautiful as the original one, but certainly as prominent, and in this case prominent, in visualizing and showcasing how impactful and dangerous thermoacoustic combustion instabilities can be to such a system. In order to avoid those instabilities, it is key and crucial to understand the underlying flame dynamics that govern a novel combustion system. Usually we have two methods to do that. On the one hand side, we have extensive experimental test campaigns, which are usually done for a lot of operating conditions. And on the other hand side, we have high fidelity numerical simulations. A lot of times we talk about LES here, where we again extract the flame dynamics knowledge. Both usually result in the same thing, a lot of money actually. They can be regarded as quite expensive. So it's no wonder that people have asked, how do we actually transfer knowledge? And with this means extrapolating and interpolating. So transfer knowledge from one operating condition to another. For example, if we change equivalence ratio or if we change the flow speed of our combustion system. With the present paper, we want to go one step actually further. We want to find out what actually happens to our flame response if we resize, so do a geometrical scaling of our combustion system as a whole thing. So let's start with our base case G equal to 1 here. We consider cases where we do upscaling and downscaling. Upscaling, basically to the right, would apply to cases where we basically have information of our lab combustor, so a lab scale system, and we want to transfer this knowledge to our prototype in action. On the other hand, downscaling here denoted by G.7, basically stands for cases where we have an operating family and we want to transfer knowledge from this baseline family to a smaller, or maybe first designs of a smaller family, which inherits information from this baseline configuration. With this, we really scale all the length scales of our combustor by the geometrical scaling factor G. So the aims or the goals of this work are kind of twofold. The first one is we want to find out, are there criteria or what do we need to take into account to actually guarantee flame dynamic similarity when doing that entire resizing process? On the other hand, we ask the question, what if we cannot keep that similarity, that flame dynamic similarity? Is there a way that we can find a scaling rule to transfer knowledge from one configuration to a resized configuration? If we talk about similarity in general, I think the most straightforward thing to do with this is to go into the non-dimensional numbers. In our case, to identify candidate criteria or candidate models that could guarantee or that could preserve flame dynamics similarity. Based on this, we then define a flame length scaling or derive a flame dynamics by some analytical measures. And then, as a next step, we evaluate actually the flame responses for the candidate criteria that we have identified in the previous step. As last thing, and that's what I've promised, we derive a time scaling or time delay scaling rule via distributed time delay models. I think with this, it's time to introduce the swirl combustion system we used in our work. On the bottom of the slide, you see the BRS combustor, which is operated with a fully premixed CH4 and air mixture. For this baseline case, we did an LES with a Whale subgrid model, the thickened flame model, and we used the BFER mechanism. This setup bases on the work of Alexander Eder and co-authors, but still we validated all of our results for the baseline case against the experimental ones obtained by Komarek and Polivke. As often already done in our group, we used system identification methods to relate input data, so velocity data sampled at a reference position, to output data, globally sampled heat release data, for a broadband forcing, in order to get the flame response for our system. In frequency domain, I mean the flame transfer function, which might be well known to most of the listeners here. On the other hand side, we use in this work primarily the the finite impulse response, which is kind of the time domain perspective of the flame response. It can be interpreted as the flame's impulse or the flame's response to a Dirac impulse forcing. And actually it contains or has the same information content as the FTF. Note that we did this methodology, or we applied this methodology not only to the base case, but also when we did the resizing, so the scaling, we did the entire same things and scaled actually the mesh within our methodology. If we do that resizing or geometrical scaling of our combustor, we need to actually take into account what happens to our operating conditions, so basically the velocity or the equivalence ratio, to name maybe the most important ones in this case. So we look actually in the non-dimensional numbers. And on the flow perspective, we have the swirl number and the Reynolds number as probably the most prominent of the group. They define basically how the flow evolves and how the swirl structures, namely here the vortex breakup or the recirculation bubble, actually appears and changes if we scale or if we change the swirl numbers in the Reynolds numbers. On the flame side, we have a look at the Lewis number, which kind of defines how thermal and the molecular diffusion happens in the vicinity of our flame. Connecting flame and flow, we usually take into account the Damköhler-number, which relates the chemical time or the turbulent timescales, in our case the macroturbulent timescales, to the chemical timescales. So by design, actually, our swirl number is kept constant as we do, or the theoretical swirl number, that is important to take into account, because when doing that resizing, the swirl number, the geometrical swirl number, does not actually change. On the other hand side, by choosing methane as our fuel, also the Lewis number is quite negligible for the case of our study. So we end up with the Reynolds number and the Damköhler number, which can be regarded as the most influential groups in our work. So let's actually do that. Just keep the Damköhler and Reynolds number same at the same time, basically. The easiest way to do so is to change the velocity in a Reynolds fashion. That means that basically our new inlet velocity scales inversely proportional to our geometry, so by 1/g. This, of course, on the other hand side, changes the turbulent time scales, which appear in a Damköhler number. So we have to adapt the chemical time scales. In our case, we do that via the equivalence ratio in order to preserve the ratio of turbulent time scales to chemical time scales. So in order to preserve, in other words, the Damköhler number. For the cases then, we do that resizing and have a look at the results. Let me guide you actually through the line of sight integrated heat release rate images, so kind of the flame images of our simulations. So you see that G is increasing here from top to bottom, but still we plotted all the flame images in a normalized format, so basically that you compare the flame length. And indeed, by keeping Damköhler and Reynolds similar at the same time, we see that, suggesting similarity, the non-dimensional flame length is preserved. The explanation for that we find in the model of Schmidt for the turbulent flame speed. By saying that for our cases, the second, so the turbulent term of the turbulent flame speed, quite dramatically dominates the equation here. We can neglect here the first part, so the laminar flame speed, and if Damköhler number is constant, this ST quite approximately scales with our turbulent fluctuations, the velocity fluctuations, which depend on the inlet speed and thus scale with 1/g. Plugging this into a relation for the flame length, we can directly see that if and only if our Damköhler number is constant, indeed the flame length scales with g, so the non-dimensional flame length is preserved. If we look in the flame responses, and on the top right here you see the impulse responses, we see that still, the time scales of the impulse response, they quite strongly differ. And that is no wonder if we say, this is normalized coordinates. So basically the bottom combustor with G equal to 1.5 is 50% bigger as the baseline case. Then, of course, it makes sense that our geometrical timescales in the end still differ a lot. The important part, if we talk about similarities, however, do they scale in the end, or can they be collapsed by one non-dimensional parameter? And for that, we suggest a convective timescale that is defined as the length basically of the flame, which is length from the backplane to the center of mass of our flame divided by our mean inlet velocity. And with that, we can indeed rescale all the peaks and troughs that we see in our finite impulse response. And this results also in a perfect scaling of the phase of the flame transfer function and as well of the location of the peaks and troughs in our gain of the flame transfer function. So far, so good. Now, from a technical perspective, you might say, interesting, but it is quite a limitation that I need to control the velocity and the equivalence ratio at the same time to ensure Damköhler and Reynolds similarity and thus flame dynamic similarity. So in the next step, what we want to do is actually boil it down to just have one controllable parameter, in our case, the velocity. That means the equivalence ratio is now unaltered compared to the base case. Again, we start with the Reynolds criterion. That means our velocity, and this is the same as shown before, scales in an opposite manner, so inversely proportional to our geometry. On the other hand side, if you want to control Damköhler-number just by velocity, what do we need to do? Actually, we just scale the velocity accordingly, so proportional to our geometry, in the end to ensure that the residence times are kept constant. When we had a look at the literature, we actually saw that people used for similar applications, they used a third criterion, and it was especially relevant for industry applications, where they just actually leave the velocity the same. This is nothing related to non-dimensional parameters actually, but because of its technical relevance, we still included this into our work. Now, starting with the Reynolds criterion cases, I want to remind you that the flame images that we see on the left-hand side, again, the physical coordinates are normalized. Nevertheless, it becomes quite clear that the normalized flame length is not preserved for the cases where we just keep the Reynolds number constant. Similar to the Damköhler and Reynolds cases we have shown previously, the impulse responses look quite similar. And note that we now included also a G.5 case, so basically a further downscale case to have a higher variability of our scaling factors. So again, kind of the time scales in which the impulse response of the flame happens, it quite dramatically differs between the 0.5 and the 1.5 case in the impulse response. So basically the physical mechanisms, they happen at later times for the upscale case. And those physical mechanisms have been well described by Komarek and Polivke, who said that the flame response is governed by two main mechanisms. On the first, we have the acoustic contribution, which travels, or which is basically the initial velocity perturbation, which travels with speed of sound to the flame base. On the other hand side, we have a perturbation in circulation due to from acoustic to hydrodynamic conversion in the swirler. But this one travels to the flame base with a convective speed. So basically we have two mechanisms with different travel speeds and thus different travel times acting on the flame response. Now, to check if we have flame dynamic similarity for the Reynolds cases is to do, or we do what we did as for the Damköhler-Reynolds cases. We basically apply a convective scaling, so a multiplication or a division by a convective timescale, in order to find if it's possible to collapse basically the impulse responses. If we do that for the Reynolds cases, we see that kind of the envelopes fall together, but not really the individual peaks, so the physical effects shaping the flame response. And this is different compared to the Damköhler-Reynolds cases that what we have shown before. And the reason for that, so basically for that difference, is what we have shown earlier, that actually the flame length, they do not coincide. So the normalized flame length for the Reynolds criterion is not preserved. The same is true if we have a look at the U criterion, so we kept just the inlet velocity constant. Again, we see that the rescaling kind of collapsed the envelopes, but the physical mechanisms have a special look here at the second peak, basically, in the impulse response. Doesn't fall together at all, basically. The reason for that is, again, just the differing flame length. So we now see that kind of the flame length do align a bit better, but still we cannot state the flame length are preserved for our U criterion here. We get a totally different picture if we go to our Damköhler criterion. Remember, where the velocity is adapted according to our geometry, thus scales with our scaling factor g. We directly see that the normalized flame length is very well preserved, and this transfers in our flame response to a perfect collapse of the impulse responses. So now all the peaks and troughs actually align. In the flame transfer function, this kind of transfers to a perfect collapse of the phase, and also a very nice collapse of the peaks and troughs, so the location of the peaks and troughs in the gain curve. Note here in the pictures or in the figures that we actually did not need to rescale our time axis in the impulse response with a convective time scale, or no Strouhal scaling was needed to actually collapse the phase curves or the phase slopes. The reason is for that, and that is the inherent nature of the Damköhler criterion defined via the velocity, that actually the residence times are kept constant. So basically the real physical time scales are the same, even if we do that rescaling mechanism. Now you still might say, talking about technical systems, it's still a bit of a limitation that we say, okay, you need to adapt the velocity in this and that way. So you're quite limited in your operability range, I would say. So this is why we offer as a last step a scaling rule, where we actually see how can we rescale the physical mechanisms based on distributed time delays. The reason why we select DTD model is because it offers physically interpretable parameters. This means we can derive scaling rules for the parameters and have physical takeaways based on the scaling rules that we find for the parameters themselves. For the two exemplary cases which are shown here, it is quite well visible that 3 Gaussian peaks are absolutely enough to get a perfect or actually near perfect fit for all of the cases, basically just by 3 Gaussian peaks. If we focus on the time delay parameters, so the taus here, it is very well visible that we get a nice scaling rule for all the parameters for all of our cases actually. I'll remind you that, and starting with the Reynolds cases here, so the squares, that the normalized flame length quite dramatically differed between the different scaling factors, so the G's, for the Reynolds cases. And this is what is visible here as well. So the normalized flame length is our x-axis here, and we see that the squares, they cover a quite broad range here in our figure. On the other hand, remember, whenever Damköhler-number was kept constant, the flame length was very well preserved, the normalized flame length, and thus they collapse here to a quite narrow spot in our diagram marked with this red oval. The main takeaway from that slide is, however, the following. Even if the non-dimensional flame length cannot be preserved, so basically if we have no similarity in the non-dimensional flame length, we still get a very nice scaling rules for all the physical mechanisms, and thus for the flame response, which gives us some predictive way to actually get the flame response for unknown configurations, just by applying the factors that we have demonstrated, or the coefficients that we have demonstrated here by the linear fits here on the left hand side. So in the present work, we have found that the Damköhler number is really the key non-dimensional group to ensure flame dynamics similarity. So if you want to keep your flame response the same, or similar, I should better say, you should really think about keeping the Damköhler number constant and preserve Damköhler number. The second part of the study was that we derived a scaling rule for the physical mechanisms, so basically for the time delays of our flame responses. That means if you cannot guarantee or if you cannot preserve your Damköhler number, we still offer a predictive tool where you can infer the flame response based on the coefficients, on the scaling coefficients we have shown in this work. What we want to use this tool for is to incorporate knowledge, for example, based on the swirler position or the influence of the swirler position, maybe as well on the confinement, and also on different fuels and operating conditions to, in the end, build a big parametric tool where we use input parameters like the equivalence ratio, for example, or actually swirler position, so on geometrical side and also on the operating condition side as inputs, and then have the flame response as a predictive measurement actually as the output of our model. Thank you.